Hey, welcome back to the tutorial. In this lecture, let's explore about FreeRTOS synchronization and mutual exclusion services. First, let's understand what is the meaning of synchronization in computing. So this I have taken from Wikipedia, which says that in computer science, synchronization refers to one of two distinct but related concepts: synchronization of processes and synchronization of data. So let's concentrate about synchronization processes. Okay, so what does that mean? Process synchronization refers to the idea that multiple processes are to join up or handshake at a certain point in order to reach an agreement or commit to a certain sequence of action. So synchronization means basically it is a following of some rules or handshaking on something to accomplish certain task. So let's take an example of two tasks over here. So one is task A. So let's say it produces some data, and task B, it always wants some data but waiting for task A to produce some data. Okay, so this is a data producer and this is a data consumer, but it is waiting for task A to produce some data. So whenever the task A, which is a data producer, produces the data, it actually sends the signal to task B to consume it. When the task B receives that signal, it comes to know that task A has some data, and then it comes out of its waiting state and it will start consuming the data. Okay, so this is called synchronization. Okay, so here task B need not to worry when the data is going to produce. It can take a rest. That means it can be in a waiting state or a blocking state, okay, until it receives the signal from the task A, which is a data producer. That means here both the tasks are agreeing upon signaling to meet one specific goal. So task A and task B are agreed upon the signaling, that task B always knows that it is going to receive a signal, so whenever task A produces data. So this is called synchronization. So in FreeRTOS or in any real-time kernel supports you to implement this kind of synchronization between task A and task B. Let's take another example, synchronization between a task and an interrupt. Okay, let's say this is a interrupt service routine which is responsible for processing the keyboard inputs. Okay, whenever you hit the key ISR will run and it will gather the data and it will then put into the queue. So whenever queue has some data, so it will indicate the task B that, hey, I got some data, now you can execute and consume the data. Let's say that task is LCD task, which actually updates the LCD whenever user hits the key on the keyboard. So here what happens is, if the queue is empty, so then the LCD task may go to sleep. It need not to wake up, right? Or it may block. And whenever the keyboard ISR runs, it will get the data from the keyboard and then it will put the data into the queue. So once the queue has some data, the queue will wake up that LCD task. Okay, there is some data available in my queue and now it's time for you to wake up and consume the data. So then the task A can start executing and consume the data which is there in the queue. So this gives a nice way of designing your application, isn't it? Otherwise the LCD task should keep on wasting CPU cycles to check whether queue has some data or not, because most of the time queue may be empty, isn't it? So this task will keep on running on the CPU and it will burn a lot of CPU cycles and have the potential to drain out the battery. So the best way to design this is let this task to go to sleep, and whenever queue has some data, let the queue wake up this task. So how to achieve this signaling, or you can say synchronization? So there are lots of kernel objects available in the OS environment. Okay, so like events, semaphores, queues and message queues, pipes, mailboxes, the unique style of signaling, mutexes, etc. So all these kernel objects are used in various operating systems like Linux, Windows, and even they are used in real-time kernels. Okay, in FreeRTOS we have semaphores. Okay, so we have both counting and binary semaphores that we can use for synchronization purposes. We have dedicated exercises where I will demonstrate how you can synchronize between two tasks and between a task and interrupt. Okay, and we have queues and we have a mutex. All right, so FreeRTOS will support the semaphores, queues and mutexes to achieve the task synchronization as well as the data synchronization. So in the later lectures in this course, so you will learn about how to use counting semaphores, how to synchronize between tasks, how to synchronize between a task and an interrupt, how to use queues for synchronizations, along with lots of code examples. So this is just an overview lecture I'm covering on synchronization. All right, so now let's see about mutual exclusion services of FreeRTOS. So let's see what is a mutual exclusion. Mutual exclusion means that only a single thread should be able to access the shared resource at any given point of time. This avoids the race conditions between threads acquiring the resource. Usually you have to lock that resource before using and unlock it after you finish accessing the resource. Okay, so mutual exclusion usually used for data synchronization. That means you have a shared resource and you have to protect it before accessing, otherwise some other task may come and corrupt that data. So that's what meant by mutual exclusion. For instance, take an example of this code. Here the counter is a global variable. That means it is global to each and every task which are in the application, and this is a function which can be executed by many tasks. This is a common function, right? So and that common function is actually making some changes to the global variable, that is counter. So here counter is actually a shared data, isn't it? These two lines of code acts on shared item, that is counter, so it needs to be protected. So we usually use mutexes to protect that access. Usually we lock the mutex before accessing them and later we will unlock them. Okay, so in this way you can guarantee that only one task will execute this segment of code at any point, so the data corruption or the race condition can be avoided. Usually mutexes and binary semaphores will be used to protect the shared data access. So how to achieve mutual exclusion in FreeRTOS? The FreeRTOS gives you two kernel objects or two kernel services. One is mutex and another one is binary semaphore. You can use either of them to implement this type of coding, that is locking before accessing the shared item and unlocking after completing the shared access. Okay, so either you can use a mutex or you can implement this using binary semaphore. So mutex is more powerful than binary semaphore. We will see all those things later, but I just wanted to mention the mutual exclusion services of FreeRTOS. In the later lectures of this course, you will learn about how to use mutex, how to use binary semaphore, differences between mutex and a binary semaphore, and we will understand all these things with the help of respective examples.